Imagine you're at your doctor and she wants to test you for a rare medical condition. This is a little scary, and it's even scarier when the test comes back positive. But before you panic, it's worth asking, what's the probability that you actually have this condition? You might think that the test tells you for sure that you have it. After all, this is a test for that condition, and you got a positive result. But it's actually not that simple. To see why, the first thing we have to do is recognize that we're working with a conditional probability. What's the probability that you have this medical condition given that you've tested positive? Given that is a key phrase here. It's letting us know we're looking for a probability conditional on something we know to be the case, or that we're imagining might be the case. The positive test is evidence in favor of the possibility that you have the condition, but it's not definitive. It's not a guarantee. Every medical test has some chance of giving an incorrect result. The test's sensitivity measures how good it is at identifying true positive cases. And then the test's specificity measures how good it is at identifying true negative cases. In real-world medical tests, these rates are often different from each other. A test might be more sensitive than specific, or more specific than sensitive. But for simplicity, today we're going to consider an imaginary test that gets 95% of the true positives right, and it gets 95% of the true negatives right. We'll call this an overall accuracy of 95%. What this means is that for a group of 100 people who do not have the condition, on average, the test is going to correctly show a negative result for 95 of them. But there will, on average, be 5 false positives. False positives are people who do not in fact have the condition, but the test gives them a positive result anyway. And for a group of 100 people who do in fact have the condition, the test will, on average, correctly show a positive result for 95 of them. But there will, on average, be 5 false negatives. False negatives are people who do in fact have the condition, but the test gives them a negative result anyway. There's one more piece of information that's important for calculating the conditional probability, and that's how common the condition is in the population at large. This is sometimes called the base rate of the condition. We said that this condition was rare, so let's imagine that 1% of the population has it. So out of 100 randomly selected people, on average, one person's going to have this condition. Okay, to do this calculation, we're going to use Bayes' theorem, which says that the probability of A given B is equal to the probability of B given A times the probability of A, all divided by the probability of B. In our case, A is you having the condition, and B is you getting a positive result on the test. So we're going to find the probability that you have the condition given that you tested positive for it, which equals the conditional probability of getting a positive result given that you have the condition. This is, remember, is the test sensitivity, times the general probability of you or anyone else having the condition. This is the base rate, all divided by the general probability of getting a positive test result, whether a person has the condition or not. This last probability can be calculated by adding up the probability that you get a positive result when you do have the condition, weighted by the probability that you have the condition, and the probability that you get a positive result when you don't have the condition, weighted by the probability that you don't have the condition. Okay, so let's start with that calculation because the other numbers can just be plugged in from information we already have. The probability that you get a positive result when you have the condition is 0.95. The probability that you have the condition is 0.01. The probability that you get a positive result when you don't have the condition is 0.05. And the probability that you don't have the condition is 0.99. First, multiply these, then add them together. The unconditional probability that you get a positive test result, not taking into account whether you have the condition or not, is 0.059. Okay, so now we have all the elements that we need to calculate the conditional probability that you have this medical condition, given that you have received a positive result on the test, which, remember, the test has a 95% accuracy. The unconditional probability that you have the condition, this is the base rate of the medical condition in the population, is 1%, so we'll put 0.01 there. Then we just found the unconditional probability that you get a positive test result. This was 0.059. Now there's one more conditional probability in the numerator. This is the probability that you get a positive result given that you have the condition, the test's sensitivity. We said that was 95%, so let's put a 0.95 there. Altogether, this gives us around 16%. So let's think about that number for a minute. Your doctor tests you for a rare medical condition and you get a positive result on the test. The test says you have the condition, and the test is 95% accurate. But even so, the chance that you have the condition, given the positive test result, is still pretty low. That probability has gone up from 1%, the base rate in the population, to 16%, but it's still very likely that you do not have this rare medical condition. One way to think about it is like this. For every 100 people who actually have this medical condition, there are 99 other groups of 100 people who don't have the condition. And the 95 true positives from that first group make up actually a relatively small proportion of all the people who will see a positive test result, most of them due to false positives. In a population of 10,000 people, which is how we're imagining it here, 100 groups of 100 each, 95 will be true positives, and 495 will actually be false positives. So does this mean we shouldn't trust medical tests? No. First of all, remember that your probability of having the medical condition actually has gone up a lot, from 1% to 16%. Second, in real-world situations, there will be other factors that play into what the relevant probabilities are for your particular case. If a doctor recommends a test for a rare condition, usually it's because you have some symptoms, or you have a family history, for example. That means that even though a randomly selected member of the public only has a 1% chance of having the condition, that's not the relevant probability for the calculation. Instead, the relevant probability would actually be the one for the population of people who have a family history or who have symptoms. You can think of this as a conditional probability of the form probability that I have the condition given that I got a positive test result and I have a family history, for example. This probability will be higher than the one we calculated here. And then third, an additional independent test will significantly raise the probability that you have the medical condition. The probability you have the condition given that you get 2 positive test results is 78% rather than 16%. And the probability given that you get 3 positive test results goes up to 98%. Still, the point stands that medical test results do err in both directions. They give false negatives and false positives. A test's sensitivity, specificity, and the base rate of the medical condition are all relevant considerations about a medical test, and these are reasonable questions to ask your doctor. This information can be helpful even if you aren't going to use Bayes' theorem to calculate the exact conditional probability that you have a condition. But this kind of question is a really good application of Bayesian statistics, since we often have information about the specificity and sensitivity of medical tests and estimates for the base rate of various medical conditions. So if you want to figure out the exact probabilities in a situation like this, you probably can.